In this one, we are going to learn derivatives with the computation graph. So we will be getting the different perspective in the term of understanding the both concept, both derivative and computation graph. So let's assume A, B, and C are these three values, and let's just combine them with our previous computational graph. So U is equal to B times C. Then we are going to combine these two things, and V is going to be A plus U, and after combining these things, we are going to get J equals to 3V. So I hope this computation graph from the previous session is clear, concept is clear. So what will happen when we do this dj by dv? That will be the question, so let's dive in. So J is going to be here 3V, right? Just as we wrote previously, and that is, let's suppose that is 11.001. Let's suppose V is 11.001 and J as being 3V, we are going to multiply that, and we are going to get value 33.003. So the value 0.001 is going to go up by some amount to 0.003, and that will be going to be the rate of change for this thing. So dj by dv is going to be 3. I hope the concept is clear until here. So let's suppose f of a is 3a, which we can write as d of f of a by dA equals to d of f by dA. That rate is 3, that thing is 3, just as we computed a similar thing before, and our J is 3V. So dj by dv is going to be 3. Now we are going to go into the concept called Markov rule. Chain rule, and we're going to move this thing here, and we're going to explore this thing now. So when in this example A, V and J, alright, so the amount of J changed when you nudge A is the product of how much v is going to change when you nudge a times how much j changes when you nudge v. So dv by dA is going to be equal to 1. This will be in proportion of the change. So I'll write the whole thing for you just to get the clarification. So dj by dA is going to be 3, which will going to be equal as dj by dv multiplied by dv by dA, and here this value is 3 and this value is 1, and multiplication of both these things is 3. So that's the chain rule in nutshell for now. So I'll dive deeper in the concept of chain rule, which I'll try to explain it more better than this terminology with some example. So hold on guys, let's just develop the intuition of the mathematical intuition behind this, and we'll dive into the more examples and more conceptual way to how to visualize the whole thing. Alright, so the final output variable is going to be, so we are going to explore the concept named as final output variable. In this we are going to, so until here we explored a little bit of back propagation as well. So what back propagation is, that also we are going to explore in this as well. So the chain rule, so I'll explain the chain rule, the concept of chain rule now. So the chain rule is mathematical concept to find derivatives of composite functions. So that's straight if we have two functions fx or gx, where gx is going to be inside fx. Let's keep these things aside for a while. So let's suppose we have two things fx and gx, where derivatives of f(gx) with respect to x, f(gx) with respect to x is given by d by dx f of gx is equal to d by dx of f of u multiplied by du by dx, where u is going to be equal to g of x. So in our example we had a function named j, where v, c, b, we had variables that depended on three variables, these three v, c, b. We wanted to find derivative of j with respect to v. To do this, we used the chain rule to break down the problem into the smaller parts. So the partial derivative is the thing that we can use to measure how function changes when the input variables change while keeping all other input variables. variables constant. In our example, we had dj by dv equal to 2v minus 4. This means when v changes by 1 unit, j goes up or down by 2 to 4 units. I hope that is making sense. We also had dc by dv equals to 0 and dv by dv equals to 2. So these partial derivatives told us how much c and b changed when v is changed. So we use these to update our overall derivative with of j with respect to v. So final output variable, that will be the concept which we are going to develop from these concepts. So in this context, our final output variable j, v, c and b is the function we are trying to optimize or analyze in the terms of its dependence on the v. So how it all came together, we started by finding the partial derivative of u with respect to v, which gave us the rate of change of dj by dv. Then we used chain rule to update this rate of change based on how c and b changed when v was changed, and we combined these updates to get our final expression dj by dv. So the chain rule is essential working with the composite functions like j, where we have these kind of variables v, c, b. Partial derivatives are useful for analyzing how functions changes when one input variable changes. By combining partial derivatives using the chain rule, we can find derivative of function that depends on multiple input variables. So let's go with some real world example just to make this thing clear. So think this problem like trying to optimize car's fuel efficiency. We have three inputs: v as engine speed, this is our engine, these are fuel things; c as a catalytic converter efficiency, that affects how well engines run, so this is a chemical thing, catalyst thing; and b is our brake efficiency, so this is how quickly we can stop the car. So yeah, so I'll just draw the car here. Now we want to find the optimal combination of v, c and b that maximizes fuel efficiency for our final output variable. So using chain rule, partial derivatives and our knowledge of how each input affects the output, we can update the optimization process step by step. For example, if we increase engine speed by 10%, then we get a rate of change dj by dv, but this is only true if we keep other inputs constant. So we used partial derivatives to find out how much c and b would need to change to maintain optimal fuel efficiency, and by combining these updates we can update our optimization process to find the best combination of v, c and b that maximizes fuel efficiency in our final output variable. I hope this made a concept a little bit more clear. So let's go in the concept of final output variable. So it is in our case j, which is the last node in our computational graph, right? So a lot of computation will be to try compute derivative of that final output variable. So final output variable is our j thing, j, which is the last node in computation. When you are writing code to implement back propagation, they will usually be same final output variable that you really care about. So in this case, that is j, which in last node in the computational graph, lot of computation will be trying to derive derivative of the final output variable, which will be d of final output variable. This is final output variable, and this is d of var variable. So in software, like when you're coding in Python, you can give whatever var name as you want. So normally what people do is give the whole thing name as a d var and dj var. So dj by dv we will consider the whole thing to be dv when we are coding, and the value for that will be 3, and the value for dj by da, we will consider the whole thing as da, and value for that will be 3. And we have done back propagation partially through this computational graph. Let's go through the rest thing. So let's write the whole thing again. A equals to 5, b equals to 3, and c equals to 2. Now combining these two, u is going to be equal to b times c, and combining these two, we're going to get v a plus u and that thing is going to be j equals to 3 times v. So all back propagation is using derivatives to go and find our way backwards in this graph. So that is how you are going to visualize the whole thing to find any of a, b or c. So when we are looking in that term, so let's suppose u is 6, v is 11, and j is 33. The infinitesimal small changes will be 6.001, 11.001, 33.003. Now we are going to have dv by du, which will be with the chain rule dj by dv into dv by du, which this thing is 3 and this thing is 1, which will result in the output of 3. So using chain rule once again, dj by dv is going to be dj by du, which will be 3 here, and du by db, which will be 2. The whole answer of this thing, this is equal sign by the way, is going to be 6. So using chain rule in this thing, b is equal to b 3, u is going to be b times c, which is going to be 6. And when we keep the infinitesimally small changes, like in this thing 0.001, then in this thing it will be 0.002. so dv by db is going to be rate of change, sorry, du by db is going to be 2, yeah. And when this goes up by 0.002, this should go like j should go up by 0.006. So the whole thing of j is going to be going up by 0.006, and v is up, or v is 11.002, and counterintuitively the j will be 33 here. I hope the concepts are getting a little bit clear. Don't worry if you're not catching up on anything, I will explain everything better. The concepts will get better as the videos will continue to come on. So j is going to be 3v, and db is going to be 6. So this is from our computation graph from earlier, the ABC 5, 3, 2, and this thing, and something in the front. So we did some derivative stuff. We got back, and we got value of db as 6, and we got value of dc as 9. We use chain rules. So what we did when we got 9, I'll try to explain here. So dj by dc is going to be, we just are using the chain rule again and again, and that is making our life easier. So try to get the intuition of the chain rule, and that will be good to have the concept. So this is 3, and this is also 3, so the answer is going to be 9. So that's how it is going to be. So now let's talk about backpropagation and how it relates to our optimization problem. So in machine learning, backpropagation is our algorithm used to train artificial neural networks. It helps the neural networks learn from its mistake and adjust its weights like V, C and B in our example to minimize error in between its predictions and actual outputs. So it is really nice and super cool thing which helps to correct the mistakes in their artificial neural networks. So think of it like a game where we want to guess a correct answer, but we keep making small mistakes. So backpropagation is like a special technique that helps us figure out which parts of our guess need to be adjusted so we can get closer to the correct answer. So how backpropagation came in? So when we were calculating the partial derivatives dj by dv, or with respect to value c du by dv and then b du by dv. Using the chain rule, we were essentially trying to find the best combination of v, c, and b that maximizes fuel efficiency, if you remember the past example. And here's where back propagation comes into play. So we had target value or expected output for optimization problem like 100 km per gallon. So this is like a correct answer we want to guess, and as we updated our weights v, c, and b using partial derivatives, we were essentially making new guess. So but instead of just stopping at these guesses, we wanted to see how far off it was from target value. So to do this, we calculated the difference between our new guess with the uh, function variable, the j, v, c, and b, and the target value. Uh, what was the name for that thing? Final output variable, not the function variable. Yeah. So this is like the error between our current estimate and the current answer. So imagine you're playing a game. When you reach a certain point on the map, you start by guessing a location, but it is way off. So backpropagation is a thing that helps you adjust your guess so that you're going to move in the right direction, and you're going to reduce the distance between your new guess and correct answer. So here's how it works. So we go back to our previous guess, the same thing, final output variable j, v, c, and b, and calculate how far off it was from target value. And we then use this error to adjust our weights v, c, and b so that our next guess is going to be closer to target variable. And we repeat this process again and again. We update our weights again and again until our new guesses are really close to the target value. So this is essentially how backpropagation helps us train the machine learning model. So imagine you're playing a game where you need to guess a number between 1 to 100. You start by guessing say 50. So calculate difference between your guess, which is 50, and the target value, let's say that is 75. So adjust your guess so that it will be get closer to target value. So repeat the same process again and again until you guessed the number that is really close to the target value. So that's how basically backpropagation works in our optimization problem, and we used to adjust our weights v, c, and b repeatedly until we find the best combination that maximizes our fuel efficiency in the example. So I hope the concepts are clear, and we are going to see how this thing is going to be used with the logistic regression in the next one. So I hope to see you guys in next one, and until then, keep learning, keep hustling.